An election is coming up in your town of population 10, and there are three candidates. A candidate wins if they are able to obtain the majority of the votes. By majority, we mean more than half the total number of votes. In our town of population 10, that's more than 5 votes. Diligently, everyone turns up to the voting booths and puts forward their vote. Now it is time to count and find out the winner. In other words, we need to find the majority element of this array. One way to do this is to store a hash map which will map each candidate to the number of votes they've received. We then loop through the votes array. If this candidate has not been seen before, add them to the hash map with a vote of 1. If they have been seen before, increment the number of votes for this candidate by 1. Each time, check the number of votes, and if it is greater than half the population, that candidate has reached the majority, so we can exit and return them as the majority element. It is also worth noting that if we reach the end of the array and no candidates have reached a majority, we can then return that there were no winners or no majority elements. The time complexity of this approach is big O of n, because for each element in the votes array, we are only performing a constant time lookup and/or insertion into the hash map. Where we can do better is the space complexity, which is also big O of n. Let's say now every person in your town has decided to run as a candidate. Suddenly, the size of the hash map grows linearly with the size of the array. It begs the question, can we find the majority element with only constant extra space? The Boyer-Moore majority vote algorithm can find the majority element with only O1 extra space. It keeps track of just two values, the candidate and the count. Here's how the algorithm goes. Initialize the candidate to be the first element of the votes array and start the count at 1. For each element after the first one, if the current element is equal to the candidate, increment the count. If the current element is not equal to the candidate, decrement the count. If the count is 0, make the current element the new candidate and set the count to 1. When we reach the end of the array, check the number of votes of the reported candidate is actually a majority. If so, return that candidate. We will do a run-through to count the number of votes from our town's election. Initialize the candidate to be the first element of the votes array and start the count at 1. We move to the next element. This element is not equal to the candidate, so we decrement the count. Now the count is 0, so the current element becomes the candidate, and we set the count to 1. We move to the next element. Again, this element is not equal to the candidate, so we decrement the count. Now the count is 0 again, so the current element becomes the candidate, and we set the count to 1. We move to the next element. This time, the element is equal to the candidate, so we increment the count. We increment the count each time the current element matches the current candidate. This element is not equal to the candidate, so we decrement the count. But note, we don't change the candidate here, because we only change the candidate if the count is 0. Again, decrement the count because this element is different. Increment, increment, decrement. Now we have reached the end, our potential majority vote is pink. But remember, we need to do one more pass to count the number of pink votes to make sure it truly does have a majority. In our case, that is more than 5 votes. It does, so we return pink as the majority element. A few of you might be wondering why we have to do that last pass through the array to make sure the reported candidate actually has a majority. This is because if there is a majority element, Boyer-Moore's algorithm will always return the correct answer, the majority element. But in the case that there is no majority element, the algorithm will simply return whoever happened to be the candidate at the end of the algorithm. In this array, no one has the majority, but if we run through the algorithm, when we reach the end of the array, there will be someone in the candidate variable, blue in this case, so we need to count their votes and double check that they really do have the majority. Since they do not have the majority, we can return that there is no majority element. Before we get to the nitty-gritty of why it works, let's look at a larger example of this beautiful algorithm. And remember the steps. If the current element matches the candidate, increment the count. If the current element does not match the candidate, decrement the count. And if the count is 0, the current element becomes the candidate and set the count as 1. Then we do our pass-through to make sure the reported winner actually has a majority. And teal is the actual winner. The space complexity is only constant extra space because in the first part of the algorithm we have just two variables, the candidate and the count. And in the second part of the algorithm, the confirmation, we only keep track of the count of one element stored in a single variable. The algorithm's time complexity is big O of n because we do one linear time pass-through to get the candidate and counts, and then we do a second linear time loop through to count the number of occurrences of this reported candidate to confirm that the candidate actually has a majority of the elements. I know that some of you still may not be convinced that this will work every time there is a majority element, and I don't blame you. I think upon first glance, this algorithm feels a little bit magical. So let's give some intuition now about why it works. When an element is encountered, its count is incremented by 1. If the next element is different to that one, the count is decremented by 1. Therefore, you can consider unequal elements as cancelling each other out. Take this case where teal is the majority. The teal element starts the count off with 1. Then the orange element decrements it back to 0, cancelling out the increment from the teal element. Then we finish with teal. So in fact, it's as if the first two elements were never there at all. On a larger scale, this means we can remove unequal pairs and it won't affect the final result, since the unequal pairs operate to cancel out each other's counts. Here we have maroon, which takes the count to 1. The second maroon takes the count to 2. Then the green element takes the count back down to 1. So you can see those two unequal elements cancel out each other. We can remove them and get the same result. Now we have another maroon plus 1 and another green minus 1, cancelling it out. This shows we can remove all unequal pairs from the array and get the same result. Let's shuffle the elements and show this again. Now we know that we can remove all unequal pairs from the array and have it make no difference to the outcome. So the question is, who remains when we remove all unequal pairs? Well, the majority element remains. If a majority element exists, that means it occurs more than half the time, or more than n over 2. But, at most, n over 2 pairs of unequal elements can be formed. Since there are more than n over 2 elements in the majority, this means there will always be at least one left over when pairing the unequal elements. This means that the majority element will always be the last candidate standing after the Boyer-Moore algorithm is complete. Anyway, this would not be a very useful coding video without some source code, so let's write this algorithm in C++. Start with defining some useful variables. N is the size of our input list of votes. We then initialize the count as 1 and the candidate as the first element of the input list of votes. We can assume the list is not empty. After the first element, if the current element equals the candidate, increment the count. Otherwise, decrement the count. If the count hits 0, set the candidate equal to the current element and reset the count to 1. When the loop is finished, we check whoever is left in the candidate variable is the real majority element by counting their number of appearances. Let's define the target to be the majority, n over 2 plus 1. If the number of occurrences is equal to the target, the majority, the candidate reported in the first part of the algorithm is the true majority element and we can return it. If we have reached the end of the loop, the candidate didn't reach the target, so we can return -1 to say there is no majority element, and we are done.